Okay, we're back. We're live. We're here. We're ThinkTech. We're at ThinkTech Talks. We're here at the SOEST show. That's the School of Ocean, Earth Science, and Ocean, Earth Science, and Technology. Okay.
Yeah.
You guys know that. Okay, and within there somewhere is geology, and we have the geologists with us. We have Sarah Kreitz and Elise Rumpf, both PhDs. Both took their PhDs only days ago in May.
Yes.
90 days, less than 90 days ago. How does it feel, ladies?
Feels great.
Really good.
Yeah.
Really
What
nice.
happened? What was it like? I mean, you have to go through a lot of schmaltz to get a PhD.
Yeah.
So, what was it like?
I'd say the final defense was much less terrifying than I expected it to
Just
be.
suppose
After-
everybody always says how
yeah,
terrifying it is.
after
yeah.
years and years of build-up, it was just kind of one more nice talk presenting my research, which was unexpected.
You too?
Yeah, I agree. It was just, you give your, in our department, you do a public defense. And so a bunch of friends were there, other students in the department, professors, my parents were there. And so it was actually kind of fun.
Parents were there at your defense.
Yeah, luckily they had planned a vacation.
That's like having your parents come to your driving test.
Yeah.
Doesn't necessarily make you less nervous.
I don't know, it kind of did for me, so
Okay,
it was
good. Good family. What can I say?
Yes, yeah.
But that means, what you just said, you're not in the same school, though. You're in different schools. You said, in my school, we do it publicly. In Sarah's school, we do it privately. I would take the private. Sorry, that's just me.
We're in the same department, so we have the same structure. You have a public defense where you give your talk to, your parents, your professors, anyone who just feels like stopping by.
People on the street.
Yeah, anyone on the
Yeah.
street.
Excuse me,
Anybody
sir.
wander in. And then after that's done, you give a 45-minute talk. People question you for as long as they can think of questions. And then all the public goes away. And then you have your private defense, where just your committee members, the people who know the most about your
And
research,
the questions
say.
are tougher because they
Yeah.
just listen to an hour of the low-hanging fruit.
Exactly.
Now we're going to drill down.
Yes. But even that was not that bad compared to writing the dissertation, handing it in. That was really the most stressful point because you have to, there's all these deadlines and you have to just produce this, 200-page document that's going to be criticized by 5 professors who are, been doing what you've been doing, but for much longer than you. And it's
But they talk about you in loving terms. One guy was here, he had a number of PhDs that he had mentored, that he had sat on, whatever it is, the committee, and it was a feather in his cap. He was so happy that he had that many in his life. He felt that each one was his own achievement. That's kind of interesting.
Yeah.
Yeah.
It's one of those rites of passage that they want you to pass. Like, no one's there trying to make you fail. But
Right.
they still want to put you to the test a little.
Yeah.
Make you jump.
Yeah.
Yeah. They want to make sure your work is quality and worthy of.
I knew one guy this was in the business area, took a PhD, and boy, they were letting him have it on format. On every word, every letter, every comma. This has happened in geology.
I had one committee member. You had Jeff
Oh.
Gillis Davis as well. He was the most thorough of all of my committee members on just making sure that the grammar and the punctuation and the spelling of everything was right. And it was really nice because, it's not that often that you have someone who reads your work with that much care.
You know what's interesting about it? You take a PhD in any field. Take a PhD in, for example, geology. What's interesting is that person is a PhD. When that person walks down the street, that person is different than the rest of us mortals. That person can read and write and speak. And you don't necessarily focus on reading, writing, and speaking when you are taking a PhD in geology. But somewhere along the way, you get it. When does this happen? In the beginning or the end?
We have a class called Graduate Seminar that doesn't focus on the writing as much, but every semester, anyone who's in our grad program has to take, or once a year, I guess, everyone has to take this class, and it's just a class where you practice giving scientific
It's a
talks.
good thing.
Yeah,
It's a good
that's
thing.
where I learned to speak.
Yeah,
I'm
me
reminded of
too.
the science fair.
Yeah.
The kids in the
little like
science
that.
fair.
Yeah, it's a little like that.
About 90% of it is being able to articulate their science,
Yeah, and then through my program, I also did a lot of teaching. So I TA'd a lot of courses, and so that gave me time in front of an audience, learning how to explain things in different terms for different people of different education levels and things. So
Okay,
Really
so
helps.
Sarah Kreitz and Elise Rumpf, both geology PhDs, and just came out of the defense. How much time goes by between the time you have this defense experience and the time you actually get your degree? You have to wait till the end of the semester or something? What?
Yeah, it basically depends on when you defend. I defended at the end of April, so it was just a couple weeks between that and graduation.
And after that, what? The beach?
Yeah. As much as possible.
Yeah, trying.
Yeah.
Now, we have a couple of minutes to the first break, but I just want to ask you guys how you got into the area of geology, how you got into the area of, you have a common thread here, and that is what? Like
The moon?
The
moon rock. Ooh, they used to sell those. Remember that?
I don't think you're
You had
supposed
gold-
to sell them.
Yeah.
They're considered national treasures. So they're not
That's why
supposed
they
to be
don't
for
sell them
sale.
anymore. Okay, well, Sarah, tell us, what did you wake up one day, look up at the sky, see the moon, and decide there was fate here?
Sort of. I actually had a kind of unconventional path to geology. I was an electrical engineer when I did my undergrad.
That's like law. You know, it never hurts.
Yeah, it's true. And it's helped me a lot through my PhD because I do instrumentation as well. But I was an electrical engineering undergrad, and I happened to get an internship for a couple of summers working at the Southwest Research Institute, which is an institute that does a whole bunch of different things, but one of the things that they do is build instruments for NASA missions to the planets.
Where is it?
There's the mothership is in San Antonio, Texas, which is where I'm from, and then there's a small planetary science group in Boulder, Colorado. So I was in San Antonio, and we were working on the Juno mission, which went to Jupiter, and I was just so excited by being in this atmosphere of building instruments for missions and thinking about this thing that I was touching and putting screws into was going to launch into space and go to
Yeah.
Jupiter one day.
Yeah, that's exciting.
And so I decided to start applying for planetary science grad school, and here I am.
Well, okay. Does the electrical engineering help you in some?
It does.
Mainly with the instrumentation.
Yeah, so I ended up working with an advisor, Paul Lucy, at University of Hawaii, who does sort of equal parts lunar science, working with data from NASA spacecraft, and development of new instruments to study the moon and the Earth. So I get to do a little bit of engineering and a little bit of science.
What was your dissertation about before we go to Elise?
It was about the surface composition of the moon and as measured by instruments on NASA spacecraft that are orbiting the moon, and what we can tell about the moon's early history, the first, say, few million years of its history, from its current surface composition.
Using instrumentation. So they say that every PhD every dissertation is a material contribution to the science. In
hope
what
so.
way was yours a material contribution to the science?
Well, for the first portion of my PhD, I took three different data sets that had been around for a few years but had never been directly compared to each other. So I used two of the data sets to sort of calibrate and improve the third data set and get newer, more robust, better mineral maps of the moon. So it told us what kinds of rocks were present where. So that was a new thing. And then the second portion of my PhD was to take those new mineral maps and then do some sort of complicated modeling to try to back out the geological processes that got those rocks there in the first place. And that's something that, at least with this data set, no one had done before.
Okay, we're going to talk about how you're going to extend that
Okay.
come September, which is very soon.
Yes.
Okay, Elise, what was the denouement for you?
I kind of fell into planetary science. I did my undergrad actually in physics, and about
Physics is, just like electrical engineering. It wouldn't hurt.
No, it doesn't hurt at all.
They're both like chicken soup. It wouldn't hurt.
And so a couple of years into undergrad, I realized that I really liked physics. I really enjoyed doing physics, but that I didn't really want to be a physicist because physicists spend all their time in labs looking at tiny minutiae of things, and I wanted to get outside. So I picked up the geology degree also. So I did physics and geology. And then after my junior year, I did an internship up at the University of Alaska Fairbanks. and at their Geophysical Institute. And for that internship, I applied to be in their volcanology program to work with volcano data. And I ended up, the man who was in charge, the professor, had read my essay, my application essay, and he said, "Oh, I think you'd be better fit in the planetary group." And I was just excited to get an internship and to go to Fairbanks for the summer, so I took it and realized I really liked the planetary science.
How could he tell?
I don't actually remember what I wrote in the essay. I think it was something about, camping and, growing up I was always camping and exploring different, my dad is a geologist, so he chose different rocks and we'd go stargazing, so it might have been talking about stargazing as a
Do you think, possibly just as a wild thought, that the fact that your father is a geologist had anything to do with your choice?
Probably.
Okay, I think we're going to take a short break now. This is ThinkTech Talks. We're talking on the SOWEST Hour. We're talking with Dr. Sarah Kreitz and Dr. Elise Rumpf, both geology PhDs, having recently done their defense and taking their degrees. Congratulations. This is a continuing congratulations through the show. Okay?
Great.
Awesome.
and we're calling this Lunar Learning, I can't read my handwriting, from the Earth to the Moon and back again. That's the title of our episode. We'll be right back after this brief break.
Hi, I'm Donna Blanchard, and I host the show Center Stage on the ThinkTech Hawaii digital series right here every Wednesday from 2 to 3 Hawaii time. I would really love to have you watch the show and see what we do here. I talk with some of the most amazing people, artists, most of them, all of them involved in some sort of artistic process. And our goal here on the show is to dig into that artistic process, and you would not believe what some people say, what some people do, what people go through to express. And these are people who have to express somehow, and I find that infinitely interesting. Not only that they have to express, but how they end up doing it. I really hope that you will watch the show and enjoy talking with some of these people the same way that I do. Thanks, and I hope to see you soon on Center Stage on the ThinkTech Hawaii digital series, Wednesdays from 2 to 3. See you soon.
And not only that, but you get...
I'm Hong Jiang, host for Asia in Review on Tuesdays.
And I'm David Day, host for Asian Review on Thursdays. Both of us broadcast our respective shows at 4 p.m.
And my topics tend to deal with questions related to environment, culture, history, and sometimes human rights.
And my shows tend to be on international business, foreign policy, geopolitics, and national security. And you can watch our shows live on the ThinkTech website at thinktechhawaii.com.
And you can also watch us on YouTube or Olalo.
So come join us on Thursdays at 4 p.m. I'm David Day.
And on Tuesdays at 4 p.m., I'm Hong Jiang.
Aloha.
Aloha.
Okay, we're live, we're back, we're ThinkTech Talks. We're here on the SOWEST show, the School of Ocean, Earth Science and Technology, and we're talking about a lunar learning from the Earth to the Moon and back again. That's pretty good title. I mean, it makes you think. Okay, with Dr. Sarah Kreitz. Kreitz? Because I put an A in there. Dr. Sarah Kreitz, C-R-I-T-E-S, okay, and Dr. Elise Rumpf, both geologists, recently graduated from SOWEST. Okay, so we're going to drill down now. We're gonna make believe that your committee's right out there behind the camera, and you're gonna explain, the very cutting edge of what you did and what you intend to do, at least at this point, the way you see it in your scientific career. You can face the camera and tell them they're the people.
Okay.
That camera, that one. Actually, that one. Try that one. Yeah.
Okay. So for my PhD, what I did was to take 2 different remote sensing data sets for the moon. So the way these are collected is NASA or other country space agencies send spacecraft up to orbit the moon. And then there are various instruments that can measure different properties of the lunar surface from orbit. So I worked with gamma ray spectrometer data, and what this does is this instrument measures gamma rays that are emitted from the surface of the moon as a result of nuclear reactions that take place in the lunar surface that take place because of space radiation that hits the moon. So it measures the gamma ray radiation, and this can tell you the major element composition of the lunar surface. And then the other data set I used was mineral maps that my advisor had actually made about 10 years ago from remote sensing near-infrared spectroscopy. So what this is as the sun shines on the surface of any object, that sunlight gets reflected off of the surface that's present there, so the minerals that are at the surface of the moon. But the sunlight doesn't get reflected exactly the same way it comes in, depending on the crystal structure of the minerals, so the way the different elements are arranged next to each other. The different minerals of the lunar surface absorb sunlight at different positions in the spectrum, so they absorb different energies of sunlight. So what you can do by looking at that sort of modified sunlight spectrum that's bouncing off of these minerals is to try to deconvolve how much of which mineral is present. But it really helps to also have an independent measure of the elemental composition of the surface. Because,
Confirmation.
Yeah, it's basically confirmation, because the minerals are made up of elements. So if you have one method that tells you what minerals you think are there, and one method that tells you what elements are there, then you can use these to check each other. And actually I was able to use the elemental measurements to sort of improve the mineral maps, because that particular wavelength range, the near infrared, which is just past what our eyes can see, that particular wavelength range is really sensitive to some important lunar minerals, but there's one that doesn't have any absorptions in that spectral range. So if you just looked at the spectrum of this particular mineral called plagioclase, it would basically be a flat slope, no absorptions at all. So it's really hard, you know it's there, but it's really hard to tell how much of it is there. So what I did was use the gamma ray measurements, which can tell me how much aluminum, iron, magnesium.
All the elements you found on the moon, all the elements you worked with on the moon, are elements that you could find on Earth.
Yep.
That's the thing, you know? I mean, wouldn't it surprise you a lot if there was something up there that was not on the table, the periodic table of elements, or something else?
We probably wouldn't know how to detect it if it were there.
Ah, okay.
We're only looking for things that
We know.
Yeah.
Okay. Sorry, I interrupted. Go
No,
ahead.
no. So I made new mineral maps, basically, that were improved by comparing with the elements. And then I used those mineral maps to try to figure out, first of all, what rocks are present at the surface of the moon, because rocks are made up of minerals smashed together, basically. And then try to do some modeling to understand what processes could have put those particular types of rocks there. And that tells you something about how the moon formed, well, maybe not how it formed, but how it evolved just after it formed. So we think the moon formed in a giant impact. Like Mars-sized body hit the young Earth and threw a whole bunch of material off into orbit.
And this was the biggest chunk of it.
Yeah, actually, that was all of this molten material and probably some chunks that reaccreted.
Reaccreted.
Yeah, they were thrown into Earth orbit.
So
and
it
then,
goes out as little pieces of flotsam, but but gravity or some process like that.
Yeah.
Physics
Yeah.
Yep.
pulls it back together again.
Yeah. So then you have this mostly or partially molten bodies, because a lot of this stuff, there's so much energy in this process that there's a ton of heat, and this newly accreted moon is probably at least partially still liquid. And so my work was trying to understand the process that formed the very first crust, the early crust of the moon, as that molten material cooled down and solidified. And then sort of the additional processes that have affected that primary crust that bring it to what we see today. So if you put up that first picture, the lunar near side and far side.
Okay, we got that picture up. There it is.
So that's just showing images from a NASA spacecraft. The wide-angle camera took pictures of the moon, basically. And what we're seeing on the right is the near side of the moon. So that's what you're used to seeing when you look up in the sky. And on the left, no, sorry, other way around. Left is the near side, right is the far side. And on the near side, you can really tell that there are some areas that are light colored and some areas that are dark colored. You can probably have noticed this with your naked eye too. So I was really interested in studying the light areas of the moon, called the Lunar Highlands, which are the remnant of that very first crust that formed right after the moon formed. And then the dark areas are the lunar maria, which is sort of more what Elise studies.
It's a good time to shift to her.
Yeah.
Okay, we're going to take a break in a little while, but why don't we start, Elise?
Okay.
Tell us, how your PhD is going to take you forward. I mean, what science are you focusing on? Because I always find, now I could be wrong about this, I always find that what you do for your PhD sort of defines at least the beginning of your postdoctoral career, doesn't it? Usually.
Yeah, usually.
So tell us how that process works with you.
How that process works. Well, for
And
my
what your science? Tell us your
Yeah.
science. Use that camera.
So for my PhD, I focused on the interaction between a lava flow and the substrate beneath it. So mostly heat transfer. So lava flow is very hot and it loses heat primarily to the atmosphere on Earth, or on the moon there's no atmosphere, so it loses heat to space. But it will also lose heat to the ground beneath it. It's going to transfer a portion of the heat and heat up the ground beneath it.
We got a
So-
picture. You want to see the picture? The lava
there a
flow
picture
picture?
already?
Yeah.
The picture is
It's a
moon
video.
lava.
Oh,
video.
but I can go into the
Whose
oh,
video is that? Is that your video?
Yes. Okay,
Okay.
let's hold off on the video for a minute.
Okay, you say when.
Yes, I will. So, right, so on the moon, the surface of the moon, so there's no active lava flows on the moon today, but about between 3 and 4 billion years ago, there was actually a lot of volcanism on the moon. And so that's how Sarah mentioned the dark spots on the moon, those are basalt flows that are very similar to the basalt flows that we get over in Hawaii, or on the Big Island in Hawaii from Kilauea. So right now, though, the surface of the moon is covered in what we call regolith. So the regolith, you've probably all seen that footprint, the picture of Neil Armstrong's footprint in the regolith. And so the regolith is this dusty material that completely covers the surface of the moon everywhere. Some places it's maybe a meter thick, but it can be up to about 5 meters thick. And this regolith forms.
Dust, you say?
Yeah, it's dust. It goes down to as fine as dust, or even like baby powder. It's that fine. But then there's larger pieces in there too. It's very unsorted and unconsolidated, and so it's just a mixture of all the different materials.
If you hit it, will it form clouds of dust?
A little bit, yes. And one problem is that it's very abrasive, so it's very rough. So when the astronauts were up on the moon, they had a big problem with this because it would kind of stick to their suits and to their masks, and so it would actually scratch, and it would cause some damage to their instruments and decrease their ability to see through their.
What were the elements involved? I mean, from the periodic table.
From the periodic table, there's a lot of iron in the lunar regolith and aluminum, so you get tough silicate materials they're very hard and small. I don't remember exactly what else. Plagioclase and.
Yeah, I mean, the minerals are basically the major lunar minerals.
Yes.
This is the ones you can see from orbit, which are mostly
Yeah.
what the surface is made of, or plagioclase, which has a lot of aluminum in it, aluminum and calcium, and a little bit of sodium. There's olivine and pyroxene, which have iron and magnesium in them, and some calcium.
Are these in short supply on Earth?
No,
No.
So it's not like we need to go up there and mine them or anything.
not for those ones.
Okay.
Yeah, there's talks about going to the moon for helium.
You guys, did you, when you were taking these degrees, and writing your dissertation, talk to each other?
Yeah, we're in the same office.
Same
or
office?
two offices.
Yeah.
Desk
Two
to
doors
desk
down.
to desk.
Well, 2 doors down, so
Okay.
different
I mean,
offices.
like
that
sharing
say-
scientific, experiences and all that. I mean,
Yeah.
are your areas close enough so that you could actually talk to each other?
To some extent. I mean,
Yeah.
I think what Elise does is really awesome. I mean, she'll tell you about it more later,
Yeah, we
but
can get
Okay,
she
well,
gets to
tell
make
us more.
actual lava. So.
Yeah. Okay. Yeah. So I'll get back to what I do. So the lunar regolith, it's created because first there were lava flows on the surface of the moon and hard rock, but then because the Earth doesn't have much of an atmosphere or even a magnetosphere, on Earth we have a thick atmosphere and we have a very active magnetosphere, and that blocks everything in space from coming to the surface of the Earth. It's very rare that we have meteorite impacts on the surface of the Earth.
Because we have the magnetosphere.
Yeah, so the
This
magnetosphere.
would be actually helpful.
Yes, the magnetosphere deflects some particles, and the atmosphere works to burn them up. So a lot of the smaller particles, that's why we have shooting stars, because they come through the atmosphere and
But
burn
not
up.
on the moon.
Not on the moon. There's no
Whoa.
shooting stars on the moon.
Oh, wow.
Right. So what happens, there's actually a lot of stuff out in space, and most of it comes from the sun. So there's, small particles that come from the sun. There's, elements like helium and nitrogen that come from the sun. There's also stuff you get material from galactic cosmic rays, things like that.
Is the moon still accreting?
And the moon is not still accreting, but it's gaining material because as these different objects come in, they smash into the surface, and these meteorites are going to add to the mass of the moon, and they break up the surface. So any solid rock on the moon is just constantly bombarded by these small meteorites, and that's how you get this regolith. It breaks it up into this fine
It's
dust.
part of the process, the regolith.
Yes.
How do you spell that?
Regolith is Regolith.
Okay.
Regolith.
Yeah, at home at dinner we speak of little else.
It's just regolith. Very
We're going to take a short break,
appetizing.
Elise. Okay, we'll come back to you.
Okay.
Okay, that's Elise Rumpf. She's a PhD, just recently graduated. And Dr. Sarah Kreitz, who's also a PhD, just recently graduated. This is ThinkTech Talks, the SOEST show. We're talking about lunar learning from the Earth to the moon and back, like a movie. You know? We'll be right back.
I'm Hong Jiang, host for Asia in Review on Tuesdays.
And I'm David Day, host for Asian Review on Thursdays. Both of us broadcast our respective shows at 4 p.m.
And my topics tend to deal with questions related to environment, culture, history, and sometimes human rights.
And my shows tend to be on international business, foreign policy, geopolitics, and national security. And you can watch our shows live on the ThinkTech website at thinktechhawaii.com.
And you can also watch us on YouTube or Olalo.
So come join us on Thursdays at 4 p.m. I'm David Day.
And on Tuesdays at 4 p.m., I'm Hong Jiang.
Aloha.
Aloha.
Okay, we're back. We're live. We're still here. We're still here at ThinkTech Talks. We wish we had more time. You know, we're running out of time. Oh.
Go for your pen.
This is the SOEST show, the SOEST hour, and we're talking about lunar learning from the Earth to the moon and back again with Dr. Sarah Kreitz and Dr. Elise Rumpf, both geologists. As we left it, Dr. Rumpf was telling us about her adventures, and we have actual movies now to play. If you
Yes. Okay. So I'll do a 30-second build-up. So I'm interested in, there used to be lava flows on the moon, and when there were lava flows on the moon, they flowed over this regolith. And the regolith, because it's been constantly bombarded from particles from the sun and galactic cosmic rays, can still hold on to these particles. And so theoretically, if we went back to the moon, we drilled beneath ancient lava flows to find these ancient regolith deposits, we could learn about the early sun and the early solar system. Now the problem with this is that the lava flow is hot and it's going to heat up the regolith and destroy these particles. So I was interested in how the lava flow is going to transfer heat into the regolith. So I did a series of numerical modeling and some experiments, and if you show the lava pour video, the first one,
Okay.
this shows one of our experiments where we actually collaborated with the art department at UH, because the art department has these big furnaces where they melt iron and bronze for sculpture.
That's
and
what I call collaboration.
Yes, my old roommate was actually a sculpture major.
See, it's all about relationships.
Yes, and so she got me into the foundry at UH, and we were able to melt actual lava and pour it into these boxes where we have lunar regolith simulant that we get from NASA Goddard, and we were able to measure the heat transfer from the lava flow, or lava pour, or it's not actually a flow, or whatever, from the lava we
Okay,
remade.
do we have
video.
did we show it yet?
Gives us an idea of the survivability of these ancient solar particles in the regolith. So if we play the FLIR video,
Okay,
this
we
one's
can play
actually
the
pretty
FLIR
cool.
video now.
So this is taken with a thermal camera.
Okay. So, okay, what does that tell us with the thermal camera?
So the thermal camera tells us the temperature of the outside of the box. So the temperatures of the inside of the box we're measuring using those thermocouples, those fancy thermometers, and then the FLIR tells us the temperature of the outside of the box and of the surface of that lava flow, which is very important because that's one of the main things you look at with real active lava flows is usually the only thing you can measure is that surface temperature. You can measure it either in the field with a hand measurement or a thermal camera from a few feet away. You can also do it with satellites. So that's one way we monitor volcanoes, is looking at satellite images of volcanoes as they're erupting to try to get an idea of the surface temperature of the lava, and that tells you a little bit about the eruption, about how much lava and how far it might go.
Gosh, you probably change your whole way of looking at things when you take a PhD like this. You're completely filled with this.
Oh yeah,
Both of you.
You have to be.
You have to be. Okay, well, I wanted to. We only have a few minutes left, and I wanted to sort of get on to the next thing, which is, what are you guys going to do after now? I mean, we're into September. Another academic year is beginning. You guys are, you're academics primarily, I guess. Although you could, get a job at McDonald's if you really wanted to. I'm convinced of that. Well, what's the plan?
Well, I actually have just started a postdoc at UH, so I'm going to stay at UH. I'm actually not in the geology department anymore. I'm in the Hawaii Institute of Geophysics and Planetology.
Interesting. Lateral, yeah.
Yeah, so that was actually, our advisors are both in HIGP, so we're sort of both in geology and in
they're cousins
planetology.
anyway.
Yeah. So now I'm officially a postdoc in HIGP, and I'm going to be working, hopefully continuing to do some of my lunar work, but my primary job right now is working on developing a new thermal infrared spectrometer. And so what that instrument is going to do, it can measure heat of lava flows, like Elise was talking about, but it also gives us that spectral information. So when we look at the heat that's emitted from rocks, they absorb heat more in some areas depending on their crystal structure, like I was talking about for the sunlight reflectance. It's the same in the thermal. So we can use this instrument both to measure heat and also to identify minerals or gases or things like that.
This is perfect. Yeah. And maybe you'll make some money. Right?
Possibly.
If you develop an instrument, isn't there something in it for you?
There could be in the future.
Yeah, the Office of Technology Transfer, according to Dr. Lasner, is changing, and they're going to change the rules about that. Maybe give you a break.
Well, I'm not the mastermind behind this technology.
Oh, okay. Well, you have to share that.
Yeah.
How about you, Elise?
So I'm taking some time now to finish up some papers, get some papers published, and I'm interested in maybe stepping away from the moon a little bit and going more into volcano monitoring and doing some disaster management. So kind of being...
There's plenty of that these days.
Oh, yes.
Especially with climate change, don't you think?
Yeah, with climate change, the number of disasters are accelerating all the time, and I think often things aren't always communicated well from the scientist level down to the community level. And so I think there needs to be some more focus there with helping communities and first responders better understand disasters and risks of the disasters. And so
the physical aspects of it, it's predictive then.
Yeah, so the physical aspects and what it might mean for them and their community and how to respond when there's a potential disaster coming up. I think I would like to help facilitate that process more.
That's great. So I guess before I get to the future, let me just get to one other thing, and that is, what were the limitations and challenges that you guys found in doing your PhDs? Where if anywhere did you get stuck? Where if anywhere did you have obstacles? Money, instrumentation. You mentioned some of the instruments didn't work the way you wanted. What else? I mean, what?
Well, actually, one of the videos I have can show this. If we play either of those time-lapse videos,
Okay.
this demonstrates. So before I did the experiments in the laboratory over in the art department, we tried to do these experiments at the lava flows in Kilauea. And so we built these boxes, we took all this equipment over to the Big Island, we hiked out and hunted down the active lava flows, and we thought it would be easy, and it was not very easy, it turns out, because the lava flows are so unpredictable that they might be inching along, and then you might think you have a good spot, because we were trying to have a box that we placed in the path of an active lava flow and then have that lava flow roll over it. And we'd again use the thermal camera to measure the surface temperature and then use the thermocouples to measure the internal temperature of the box. And if we show one of those videos, you can see that it didn't really turn out as expected because the lava flow can stop. You can think it's coming and it can stop before it gets to your instrument. Or one time we put the box out and the lava flow broke open.
This is a video now
faster.
of lava flowing over the box.
Yes. The cool lava. But yeah, that went by quickly, but you can see that one was actually very vigorous, and we did get our box covered up by the lava flow, but it destroyed all the equipment so quickly that we did not get any data.
Too bad.
It was a great proof of concept that we could go get one of these boxes buried by a lava flow and theoretically get some information out of it, but
It's like the
it's
flight
difficult to
path
get
recorder.
Yes, and it's difficult and expensive to find equipment that will survive temperatures that high.
And then do it again and again.
Yes, exactly.
So Sarah, what about you? What limitations and challenges did you have?
Well, one of the limitations is also sort of instrumental for me.
Instrumental?
Yeah, exactly.
I love that.
I was working with data from NASA spacecraft, but I was actually working with pretty old data from the 1990s. And so the instruments at that time, especially the spectrometers at that time, couldn't measure with as high spatial resolution. So the pixels on the moon, the area of a spot that we could look at on the moon was about 100 meters by 100 meters with the spectroscopic technology of that time. Whereas just as I was finishing my PhD, there are a whole bunch of new beautiful data sets coming out with, even down to meter scale imagery of the surface of the moon. So I would have liked to get my hands on some of that new data. But actually, my sister grad student, my advisor's other student, is working with some of the new, really exciting high spatial resolution data.
Okay. How long did it take you guys to get your PhDs? I mean, from the time you started working on it, I guess after your master's degrees?
We both skipped master's degrees.
Oh, you can do that?
Yeah, in our program, you don't have to have a master's. If you don't have a master's coming into the PhD program, you have to do an extra qualifying exam. So the qualifying exam was writing about a 10-page paper and then presenting it just in front of a committee of 3 professors. And so it's rigorous and it gives some extra time, but it means that you don't have to, it's not as long as the 2 years it takes to get a master's, but it's just to show
So how
that you
many
can do the
years
work.
then? How many? 4?
I took 7.
7.
Which is a little long, but
If you could do it
That's
again,
stuff.
would you do it faster or slower or the
Ooh.
same?
That's a tough question. I don't know, I enjoyed my time in graduate school. It's a good time to expand your knowledge and you get to work on, I was lucky that I was able to kind of develop my project where I wanted it to go. I wasn't, some people come in and their professors have an exact project lined up for them and they do, where they have grant money and the grant money is paying for them to do this project, so they have to do it, what they're told essentially. But I had the freedom to I had my own funding for the most part, and my advisor gave me the freedom to kind of study what I wanted. And so that was great because I think I had a very good knowledge base, and I was able to expand to a couple different specialties.
What about you, Sarah? How long did it take?
I took almost exactly 4 years, which is a little on the short side for our department. And I probably wouldn't have graduated as fast as I did, but there was this postdoc opportunity available with a professor I had worked with, and he was like, if you really rush things and finish up, you can work with me on this project. So I was really excited to do that. And I actually ended up not doing a project that I had intended to do for part of my PhD because I just didn't have time. So I don't know if that project will ever get done now.
You guys, will you take other degrees later? Or is that sort of not in the cards right now?
I don't know. After 7 years of graduate school, I'm kind of done with degrees for now.
That's what I said after a master's in law. That's what I said to myself.
Yeah.
The same. You too, Sarah.
Yeah, I feel pretty content with the amount of school I've done so
Perfect
far.
choice of words.
Pay off
Well-
student loans and then decide if to go back.
We'll talk again in a year and see how you feel.
Yes.
Well, that's Sarah Kreitz and Elise Rumpf, both PhDs recently in May of this year, and now they're going on to the next phase of their careers. Congratulations again, you guys. This is ThinkTech Talks, the SOWEST show, the School of Ocean, Earth Science, and Technology. We've been talking about lunar learning from the Earth to the Moon and back. It's been great. Wish we had more time. C'est ça, c'est tout. Aloha.
Aloha.